Many of you have likely used text to generate fantastical images, for example, using systems like DALL-E. And so the question is, what else can we use text to generate? Can we do text to drive, for instance? Why might we want to do text to drive? Well, imagine that in the future, your car can be your friend, and on your drive home, you can tell it to detour by the supermarket to pick up cat food. Or imagine that you need to look up an address, and then you just tell your car, take over. Or you might even tell your car to take care of errands while you sleep at night, maybe to go refuel itself. Well, these are extraordinary possibilities that we can now imagine we could have with self-driving cars. Today, we can turn text into fantastical images, but to turn text into commands that are executable and that a car can follow correctly, we need to do so much more. We need to think about physics. We need to think about geometry. We need to think about the rules of the road. So all of these are coming together in our project to do text to drive. Now, in order to do text to drive, the first thing we need is a car that can execute these commands. And so that means a self-driving car. And today you can take any wheel-based device and turn it into a self-driving vehicle by following a recipe that is, it's frankly followed by many research groups around the world and also many companies that are building AVs. And so here's how it goes. You start with a vehicle platform that can be driven using drive-by-wire. You add to this platform some sensors that can be used to measure the world. You write some software for perception, and this can be used to make maps and to figure out where the obstacles are. You write an estimation model that helps the car figure out where it is, usually by looking at the infrastructure on the road. And then you build some planning and control modules, and all of that together will turn your car into a self-driving car. So pretty simple, right? Well, we have algorithms to execute each of the tasks that are needed for a self-driving vehicle. But the solutions we get are relatively brittle because they require that we explicitly program each type of road situation that we encounter. So you have to carefully engineer parameters for nighttime driving, for daytime driving, for driving in rain, for driving in sunshine, for driving on roads with lane markers, for driving on roads without lane markers. And so this gets to be tricky. Now, in our field, we can achieve increased robustness by using machine learning to learn from humans how to do this task, to teach robots to learn from humans how to do the task. And the solution is to learn a representation of what a human did in similar situations. And this can be done by building end-to-end machine learning systems that aim to optimize a single learning algorithm, which directly takes us from raw data onto control signals. And we have solutions to solve these problems. Now, these solutions need data. And specifically, they need driving data that is collected from humans on how they drive. Then we also need a machine learning model, and we need opportunities for physical deployments. Now, it's easy to collect data for normal driving situations, but the difficult aspects of autonomous driving are deciding what to do in accident or near-accident situations. And this data is difficult and costly to generate. So what can we do? Well, collecting data for near crashes or safety-critical scenarios is not feasible to do directly from the human drivers, but we can generate it in simulation. And the way we have solved this problem was by creating a simulation environment where we collect one data set from a real human who drove a real car. And then in simulation, we can turn that data set into anything we want. We can turn it into erratic driving. We can turn it into accident or near-accident situations. And so since this is done in simulation, it's okay. We don't have to destroy the vehicle. And so here's an example of original data, a very boring drive down the highway. And here you can see erratic data that is now stimulated by our system. And with this approach, we can train self-driving vehicles to cope with challenging driving situations. And we can teach the vehicles to do so in simulation, and then we can take the learned policies and deploy them directly onto autonomous vehicles. And here's an example of a policy that was trained in simulation and that is now driving our vehicle in a completely new environment. And we can look a little bit under the hood, and here you can see the feedback into the car. This is its camera. At the top right, you also see the GPS location of the vehicle, and then you see what's happening inside the car. So this is really cool because it gives us more robust autonomous vehicles. But even though we can cover a wider range of road situations using the simulation approach, we still cannot imagine everything. Because even with a simulated approach, we have to explicitly say, oh, these are the kinds of situations we want to model. Driving in the rain, driving in sunshine, driving on country roads, driving on highways. And so the question is, can we get our vehicles, can we get our robots to understand their environment to the point where they can drive anywhere? Because if we can do this, then we can also begin to talk to our vehicles and give them commands in language, just like we give to a friend. And so the answer is yes, we can begin to make headway in this direction using language-based planning and reasoning. And this can be achieved by connecting the world's knowledge to visual-based learning systems that can keep the car in lane. So how does this work? Well, the physical perceptual system of the vehicle can be connected to textual descriptions that represent abstractions, such as snow, sun glare, tree, or any other abstraction you can express into a word. And then we can take these descriptions and we can reason back and forth between them. We can reason in the language space and we can reason in the visual space, and we can move back and forth between these representations. And the end result is that we end up with systems that allow us to reason about camera input streams using language. And this allows us to generalize the car response to new situations that the car hasn't encountered before in simulation or in the real world. So here's an example. Let's say we have an image of a country road with a deer in the middle of the road. We can augment this image with a description, with a textual description of what this image represents. And then we can build a foundational model that aligns the perceptual features of the image input with language features. And this alignment allows us to do this back and forth between reasoning in the language space and reasoning in the visual space. And this is exciting because now we can begin to talk about intelligence as not just the connection between perception and action, which is the way we used to think about robots, but as the connection between perception, language, and action. Where with language, we have the ability to elevate the level of reasoning of the vehicle and the level of interaction between the human and the vehicle. When we connect perception and action, we can do extraordinary things, but they require that we think about pixels, that we think about XYZ coordinates. We do not think about concepts like deer and road and sky when we connect perception and action visually. When we introduce language, we can begin to teach our vehicles to think in the same kind of abstractions we're used to use. So here's how this works in practice. First, we find a set of textual features that are relevant to driving. Then we curate textual features that can be swapped with visual features. And finally, we have the ability to stimulate image features by sensibly swapping in textual features. So what this means is that I can train my autonomous vehicle to avoid deer. And then with language, I can say, now also avoid trees and cars and people and just about anything I can express in language. And so the training and the learning of the vehicle becomes much faster and much more abstract, much more logical. So here's this idea working in practice. This is an example of training data for our autonomous vehicle. We have a rural road in the summer, it's dry, it's daytime, we have a single car on the road. And so this is how we train the policy. And now with language, we say, avoid the deer. We can say other things. We can also say, now drive in at night, or drive in snow, or drive in rain. And this is really extraordinary because it's truly accelerating the way in which our autonomous systems can understand the world and respond in a correct way to the world. So with this approach, we are ready to tell our robot cars to detour by the supermarket to pick up cat food, and we expect our cars to figure out exactly what to do, exactly how to do it. And we can even do other things. We can even get our cars to understand complex road situations that they have never seen before. For instance, the case of a plane landing on a highway as an emergency landing maneuver. So the bottom line is that by connecting language with perception and action, we elevate the level of reasoning of autonomous systems. And we get them to a point where they are much easier to interact with. We can interact in natural language. We can expect responses from the vehicle that meet the physics laws and the rules of the road and common sense. And all that will take us into a world where we can begin to view our cars as our friends. Thank you very much.